Okay, I think we can get started. I think it's after 2 o'clock. So today we have Chris Kummerow. Chris is a professor of atmospheric science at CSU, where he has also served as director of CIRA. He received a PhD in atmospheric physics from the University of Minnesota in 1987. Research interests include remote sensing, the global water cycle, and its uncertainties, including how the uncertainties relate to physical aspects of the atmosphere and thus the fundamental processes underlying precipitation in the water cycle. Before CSU, he was at NASA Goddard. He was at NASA Goddard as a project scientist, the project scientist for the Tropical Rainfall Measuring Mission, TRMM, and the study scientist for the Global Precipitation Mission, GPM. Chris is currently the team lead for GPM's passive microwave algorithm team and the team lead for advanced microwave scanning radiometer science team. You're a team player, I guess, right? Team leader, right, and team player. Chris currently co-chairs the International Precipitation Working Group, has been the chair and member of the GWEX Data and Assessments Panel, a member of NASA Earth System Subcommittee, and is currently co-chairing the midterm assessment of the 2017 Decadal Survey of atmospheric science, of Earth observation from space. So Chris is a renowned scientist in the field. He was awarded the NASA Goddard Exceptional Achievement Award. He's an AMS Fellow and most especially Professor of the Year at the Department of Atmospheric Science for 2023. So
that's all that matters.
Thanks so much.
All yours. All right. Thanks. So thanks, it's good to see a lot of people I've known over the years. And talk today about satellites and precipitation, sort of as I start getting older, starting to reflect on what have we actually learned in the last 30 years. And it turns out we've learned some stuff, and I'm supposed to wear this microphone in case I wander away from the podium. Okay, 1, 2, yeah, it works. All right, so just as a way of introduction, and I'll come back, okay? There we go. So we're going to talk mostly about 2 satellites, which is the TRMM satellite on the right. It was the first spaceborne radar for precipitation. It's a big 2 by 2 meter antenna. And then the other instrument there's the TRMM microwave imager, which is sitting there. Were sort of the main instruments. There was also a lightning sensor, visible infrared sensor, and an energy that sensor series that failed right away. But the key instruments were the radar and the radiometer. And so that was in a 35-degree inclination orbit, tried to get tropical precip, quite successful. So we said, well, let's go global. And that was the Global Precipitation Mission, which really has copied the design. There's a second radar on there. Instead of just using 13 gigahertz, we went 1335 to get more sensitivity to light precip. And then we made the radiometer a little bit more capable. But essentially it's a copy that goes into 65-degree inclination instead of 35-degree inclination. So that'll be sort of the focus, but I thought I'd sort of give you an overview. We're going to first talk about the various products that are out there. Okay. And because precip it's not only for research, has a lot of sort of applications as well. There's a lot of products out there. Okay. So we'll talk very briefly about the radar products, IR products, passive microwave radiometer products, and then what's been done to validate any of these. Okay. And then we'll put it all together into what's known today as sort of the precip products, and ask how good are they, what are they good for, what are they not good for, okay? So let's start with the GPM radars. They're big monsters, okay? The radar is the big shiny plate you see there, okay? And I think they chose really small people on purpose to make the radar look bigger, okay? But why do you need such a big radar, right? Putting big things in space is very expensive, okay? Why do you need such a big radar? You need such a big radar because it's microwave. And just like light spreads when you put it through a pinhole, so there's microwave. So the size of the hole sets the spreading, and the antenna acts just like a hole. So the bigger the antenna, the finer the spatial resolution. And with a 2 by 2 meter antenna, it's actually 2.2 by 2.2 meters. At this frequency, you still only get 4.5 kilometer footprints on the ground from a 400 kilometer orbit. So the satellite's really low, and the footprints are still quite big with that big antenna. If we were Department of Defense, we would have put a 10 by 10 meter antenna up and spend $1 trillion, but we're not, so that's as big as you can get, okay? So how well do they work? Okay, we have two of them. Let me just sort of back up. There's two radars. There's the big radar you see, that's 13 gigahertz. The 35 gigahertz radar is the one right behind it. That's covered in the black plastic there at the moment. And that was supposed to be more sensitive. It turned out not to be so. When they built the radars, the two radars, the KU radar, the 13 gigahertz, ended up way more sensitive than it was supposed to be. And the high frequency radar ended up being less sensitive than it was supposed to be, so they're equally sensitive, okay? So we didn't get anything very much out of it, you know. But how good were they? Oh, let me also, before I show you how good they are, radars have a fairly narrow swath, okay? And that's dictated just by geometry. If you have a 4 kilometer footprint or a 5 kilometer footprint, if you try to swing out to 45 degrees, part of that beam is still hitting the ground, which is where all the signal comes from, you know, over the air. So part of the beam, so the first 3.5 kilometers are blind. They're just dominated by the ground echo. So if you want really to scan wide, you have to have a very small footprint. With 4 kilometers, we're sort of limited to plus minus 15 degrees. So it's a fairly narrow swath. So in validation against the ground-based radars in the US, okay, what they did is coincidence only, so it's not a rain accumulation. It's only when the radar's coming over, which is roughly every 8 days or so. You take the two rain rates and you add them together. And then what they did in this plot is they took latitude bands from 25 degrees, so southern Florida, all the way to the northern border on the right. And so it's 1 degree strips of latitude. And that's just to get enough sampling to kill the random noise. But when you do that, the dashed lines here are plus minus 10%. And you see the radar, by and large, gets you within 10% of the ground base, okay? So that's really good. You can never get two rain gauges to agree to 10%, even when they're sitting next to each other, okay? They did the same thing over Japan. Instead of taking latitude bands, they took those different regions to get enough sampling to reduce the random noise. Okay? But again, you see the 10%. Okay? So that's all really good and fine. But then when you take a closer look, okay, and this is the ground-based, this is a spaceborne radar versus the ground-based, and this is now a map. We didn't average over all the same latitude. You sort of see it roughly, those hexagons are by radar. And what you see is that, there's differences in the country, okay? The West Coast tends to be, Intermountain West, I should say, is mostly reddish, okay? The coastlines are blue. That's because, ground-based radars don't work well once you get beyond the coast. But the Intermountain West is mostly red in 1919, 1920, but then in 1921 it turns hard blue, okay? I'll give you a preview now. That's actually the ground-based radar changing, not the spaceborne algorithm changing, okay? Very subtle things, but it's very difficult to validate because people with ground-based radars like to play with their toys. And that means that they keep changing the story. Okay? So just when you think you know what's happening, you get something different. And then you get to spend the next couple of years trying to figure out what it is that changed. Okay, so those are the radars. The validation depends on where you are and when you do it. Let's talk about the radiometers. This is a sort of only sciencey slide I'll get you. This is the dielectric properties of water, okay, that everybody should know. Okay. Real part, imaginary part. Imaginary part of the dielectric constant is what causes absorption. Okay. This is the line, and absorption is actually this epsilon double prime divided by the wavelength. So this is the visible radiation, okay, 0.1 to 1 micron. So right here is the visible, almost no absorption, okay? And you know that if you go to the bottom of a pool, light still comes through, right? It's not absorbed. Then you get to the IR, and you get a lot of absorption, particularly at the peaks. Okay? And then even with solid water, there's tons of absorption. But then it sort of flattens out while the wavelength keeps increasing by a factor of 10. The microwave is about here. So a microwave only has about 1% of the absorption of the infrared. And that's for liquid. And ice has even 2 orders of magnitude less absorption in the microwave than the liquid does, right? If you don't believe me, just put an ice cube in your microwave, turn it on and see what happens. Nothing, okay? The ice cube is perfectly happy sitting in the microwave. But you gotta keep the water dripping off of it, right? Otherwise the water boils and melts the microwave, okay? So these things become important in a second. First with the infrared, okay? That's really, everybody's seen infrared images. Here's a tropical cyclone. If the most commonly used infrared rain algorithm is the Gauss precipitation index. If temperature is less than 235 Kelvin, rain rate is equal to 3 millimeters an hour. And if you're over land, you multiply by 2. Okay? That's the algorithm, time tested, proven to work. Okay? Okay? So that's it. People have tried to improve on this. It's hard. Okay. Here's the microwave radiometer. Okay. You see that the antenna is not nearly as large as the antennas from the radar, so the resolution is not as good as that of the radar for the same frequency. Okay. So let's talk a little bit about passive microwave first, because the signal is a bit more difficult to interpret. So these are the same scene. This is South America. Buenos Aires, Rio de la Plata is here. Okay? And so at 5 different frequencies. So what we know is that absorption increases as the wavelength increases, right? Because absorption, right, is over the wavelength. Okay? So as the frequency increases, the wavelength shrinks and absorption increases. We also know from the microwave that the oceans, the radiation coming from the surface is equal to the emissivity of the surface, which happens to be really low in the microwave, times the surface temperature. The surface temperature is the same, irrespective of frequency, but the emissivity is also changes dramatically from ocean to land. And it's only about 0.5 over ocean, and it's close to 0.9 over land. So over ocean, you see temperatures of 150 Kelvin if the surface temperature were 300, right? Half of 300 is what the signal appears to be, whereas land is much warmer, right? So you see the dark ocean, you even see the river. There's enough water to make it lower, right? And then you see this out here, which is clouds, right? Which absorb the radiation from below and then emit at their own temperatures. Right? So the atmosphere is sort of partly transparent at this frequency, and you get a mixture of the background and the cloud itself. As you go up in frequency, you see this emission signal increases, fairly substantially. Here again, which is a bit of a water vapor absorption band, as you go higher, you start seeing this, greater and greater absorption. You also start seeing these little blue dots over land. And that's the ice scattering, right? So radiation that's coming up from the liquid now runs into the ice, which is almost a pure scatterer, and reflects some of the radiation back down to the surface. Okay, so we have all of these things going, and after you've worked with this for 30 years, you can look at an image and pretty much draw what's there, right? But if you've only been sitting here for 2 minutes, it might be trickier, okay? Right, but we have emission and scattering going on over oceans. It's mostly an emission signal that you're looking for, because it's directly related to the liquid in the rain ultimately. Over land, you don't really see much of an emission signal because the land is warm to begin with. And what you really see is a scattering signal due to ice. So any precipitation over land from the microwave is related to the ice, not so much the rain. Okay, so we've done this. So now let's go back about 20 years in history. And people were busy making these products. And this is the Global Precipitation Index, that complicated equation of, it's always 3 if it's colder than 235. This is it's an annual average precip over the Western Pacific, right? So Australia being right there. And then, because it's an algorithm, they took a bunch of rain gauges on the atolls in that region, and they validated it. And the mean's about right, but they overestimate a little bit at the light end and underestimate a bit at the heavy end. But overall looks okay, right? There were other people who were using microwave, and the first microwave instruments were microwave sounders for temperature and humidity sounding. And they used some of those channels, and they made the algorithm of the emission signal. And they made their map, and they validated against some atolls, and they said, this looks good, right? And a little bit later, there are people who were using passive microwave imagers that have the lower frequencies. These are the frequencies I just showed you. And they made rainfall maps, and they validated against atolls. And so everybody's sitting there going, we have at least 3 viable methods. They all agree really well with the atolls. Until you put all 3 plots together, right? And you say, wait a minute. Where the IR says it's raining a lot, the sounder says it's hardly raining, and vice versa, right? And so this is sort of the first slide where we always joked is the algorithms are perfect, the clouds are making a mistake, okay? Right? So when you think about this, right? It's actually, let me just sort of, I think I have this in the next slide. We're over oceans, so there's emission, right? And the more liquid there is, the more emission there is, right? But you assume a certain amount of ice which depresses that emission. When you have more ice than that, then you depress, there's an excess depression which the algorithm interprets as less rain. When there's less ice than normal, there's excess emission, and the algorithm says, oh, it's raining really heavy here, right? So when we go back to here, right? The IR is pretty straightforward. That's where the cold cloud tops are, okay? That's not actually rain, that's just cold cloud tops. That's where they live. The sounder, right, is fairly high frequency, so it's really sensitive to the ice. So any place where the warm rain processes dominate, it loves to make extra rain there. So it makes rain right there in the Central Pacific, where the IR, in fact, says there's no cold clouds there because there's no ice associated with the rain. Okay. So that's where it loves to make the most of the rain. And then the imagers, people actually sort of already knew by then, is sort of the happy medium between those. And it's actually a much more robust signal than either one of those is. Okay. So it's not a question that the algorithm, the algorithm is just not accounting, or at this stage, was not accounting for changes in the cloud behavior, right? That the amount of ice in the clouds was screwing up the retrievals. So from that, what is it that we do, right? So we do a Bayesian algorithm where we actually use the radar on the TRIM and later on the GPM to tell us what the cloud structures are that are actually observed globally. So we just make a huge database, it's 300 million entries of every cloud that was ever observed, along with the computed radiances for any given sensor. And then all the algorithm does is says, look, given the observed radiances, what does it look like the most? Okay. And it just pulls the things that look closer, gives them more weight, and basically is looking for, I've seen this before, or something very similar to it, weights those things equally and comes up with an answer. It works fairly well. Here's sort of an early example of it. Here's the radiometer only answer of a tropical cyclone. And here's exactly the same thing, but through the middle of the radiometer where the radar lives, I just superimposed the radar image of that, right? And so if you look at the bottom, you can barely tell, the radar has higher spatial resolution because it's got a bigger antenna. But beyond the size of beyond the resolution, the two of them actually look very, very similar, right? So the radiometer, if you teach it properly, learns from the radar and sort of becomes almost as good as the radar. Okay. So now we can validate the radiometer algorithm against the ground-based radar too. This is the slide I showed you before. Okay. These are two different radiometers. We actually did this when we were improving the version number of the algorithm. And you can see that from the old algorithm to the new one, the colors are a little bit more faded. So we match the ground-based radar a little bit better. But you also see that the radiometer sort of matches the radar product, right? And that's really because it's trained with the radar product. Right? So whatever mistakes the radar makes, the radiometer is happy to learn from that, okay? And happy to reproduce those errors. Right? So we do this, but we do this on a global basis, right? Lots of people try to do this, especially with machine learning now. You train the algorithm on the ground-based radars over the US, and guess what? They make every rain system look just like rain over the US, right? And they bias the whole global thing quite significantly, because global rain does not look like, Oklahoma, where people love to train their things because the radar data is good and plentiful and easily accessible. Okay? So people these days are happy to turn everything into Oklahoma. Okay? But so anyway, we see that we're sort of copying the radar, and then we make the same sort of mistake out here, which is what got us to say there's no way that the radiometer is making exactly the same mistake in time as the radar. It must be the ground-based. And then eventually they sort of figured out, I'll talk about that in a second. The reason that they make a mistake is super subtle. Okay, so this is the operational radar product. It's a combination of radar and rain gauges, okay? So you have your radar, except radars need to be calibrated by gauges. So they use the gauges. But you have to be very careful when you calibrate radars with gauges when there's not enough data. If the data is not robust, you amplify the error, right? So for instance, if there's a rain gauge here that even though there's only a little bit of echo, says there's 100 millimeters an hour, if you're not careful, you will turn the whole country into 100 millimeters an hour, or say there was no radar echo, but a gauge said 100 millimeters an hour. You don't want to turn every no echo into 100 millimeters an hour. Right? So you have to be careful with what you call a robust adjustment. And people keep tinkering with how to merge the radar and the gauge data to be robust and with as high a time resolution as you can. And that's what the radar, they just did that. In the Mountain West, they put a little bit more weight on the gauges and took a little bit of weight away from the radars. And all of a sudden you have a 15% change in the total rainfall that accumulates, right? So it's that subtle. And for those of you who think that 10-15% is a big problem in global precip, let me just talk about gauges for a second. There are two big gauge, there's actually three, one of them I don't have, but one of them is the WMO, the GPCC, Global Precipitation Climatology Center. They collect, these are the data, so it's fairly dense over the US and Europe, less so elsewhere. The Climate Prediction Center of NOAA also has a gauge network. It's almost the same gauges, okay? It's not different gauges that they operate. They take the same gauges in more or less, and then they interpolate it to make a new gauge map, okay? So these are gauges, that's the truth. Okay, so in this slide, the circles, which are the open circles, black at the top, that's GPCC. The open triangles, which are sort of at the bottom of the plot, that's CPC, okay? They're about 20% different, 25% sometimes different, okay? So those are the two same gauges, different analysis, okay? They differ by that, and then all the solid lines, I just put them on here. There's a number of satellite products now that after they're done with the satellite, they still merge in gauge data to unbias them. And what's really obvious from this figure is which products use which gauge product, okay? So all the top lines all use GPCC as a reference. All the bottom curves all use CPC as the reference, right? So you have 20% differences in satellite products, not because they differ in some fundamental constant, but because they use a different reference for their gauges, okay? So that's sort of where we're at, right? Spaceborne radars, we've done lots of experiments that have really high correlations with ground-based radars, right? But ultimately it's a radar versus radar. Why shouldn't they correlate really well? We still get regional and temporal biases, even in the radar, right? Even when the ground-based radar is stable, we do see differences from place to place. And that's because the ground-based radar still tune themselves to gauges. So it's more directly related to the surface rain.
Project for a minute.
Yeah.
So you said that the two rain gauges right next to each other measure different things.
Often do, yes.
Often do. And
Yep.
so is right. But that looks like a systematic difference between those two sets of rain gauges.
Yeah, so this is not so much the two different rain gauge analyses is not so much the rain gauge itself as what they do when there are sparse rain gauges and how they interpolate between gauges. Right? Okay. So it's not so much the gauge's fault as the humans doing the analysis thereof. Yeah. So again, radar's really solid. Passive microwaves, the imagers are better than the sounders, particularly over oceans, because they see that emission, the lower frequency is better for the emission. They've been sort of, these days, we're getting pretty good at training them on the radar. So they're of comparable quality, okay? IR don't have very good quality at all, okay? But IR, because of geostationary satellites, is always there, right? So when you have a radar that only sees a spot every 8 days, compared to a geostationary IR, that the technical term is, I think, sucks in terms of rainfall, but always looks at the scene, right, and says, tall cloud, let's put some rain in there, right? The IR actually wins after a month, okay, just because it's always there, right? But from sort of 20 years of doing this, or 15 years of doing this, the community sort of agreed what we really needed to do is use the passive microwaves to get the rain, and then use the IR to advect the rain between passive microwave overpasses, right? And that's sort of what's done. There's a ton of passive microwave radiometers flying today for various reasons, none of them for precip, okay? But they're flying, and we can take their measure. We can take the observations. So in here we have, so the GMI, which is the GPM, in the TRIM, this was a short period when both satellites were there. That's these two, the two narrow ones, because they're pretty low altitude. All the big ones are, AMSR is a Japanese instrument that they use for various purposes, ice, snow, sea surface temperature. The SSMIs, which is the yellow, is a Department of Defense sensor that they fly for various sea states, in fact. MHS, which is the dark yellow, is a humidity sounder, okay, which NOAA operates for weather forecasting purposes. But all of these sensors are there all the time, right? This is a 30-minute window. The rest of it is sort of filled with IR, okay, between the overpasses from the microwave. And this is what you get, okay? So when you put all the microwave and all the IR together, this is sort of the state of the art. It's 30 minutes, soon to go to 10 minutes once all the global products are homogenized to 10-minute data. And it's 10 by 10 kilometers, right? And you can watch this and it looks quite reasonable. If you pay attention and sort of defocus a little bit, you see it flickering a little bit, okay? And that flickering comes because the passive microwave is there, and then the interpolation happens. And that's not quite as smooth as people would like, right? So that flickering happens because the passive microwave is not completely agreeing with where the infrared, wants to move things, or there's two passive microwaves that disagree and the infrared can't quite interpolate between them. But to the extent that features are smooth, that means everybody's agreeing on what the precip is, and the IR is moving things along. Right? So these things are fairly robust these days and get lots of usage. Okay? That I just showed you one, but there's lots of these, right? And everybody's using more or less the same technique. Okay? Rely on the microwave for instantaneous rain, rely on the infrared to move things along. Some of them morph, some of them move it, advect it, so different techniques, but they're all more or less the same, right? And they all more or less agree on what the global precip is and how it's distributed. And actually one of these, we're starting to see, people keep asking us what the trends are, and in the OBS, there's no trend visible yet, okay? The change of global precip with an ENSO is big enough that the number of ENSOs completely hides what trend there ought to be in precip. The one exception is sort of the ITCZ, which in fact is strengthening. Right? And this is the 2023, so this is very current, okay? Big El Nino happening. And this is the precip anomaly is on the right panel there. And the ITCZ is really much, much stronger than it normally is. And if you plot just the ITCZ since 1980, which is sort of the beginning of these products, where we go back and reprocess it, you can sort of see the strengthening of the ITCZ. Amount of rain that's falling there is in fact, and it's really robust. And you still have the El Nino signals, okay? But it's a fairly robust signal that's coming out of everything. So that's robust. We're still trying to validate things. There are programs underway that sort of every day look at these, composite products, accumulate precip for a day, compare it to gauges on the ground, and then, do statistics. And I can tell you that almost nobody's looking at these, okay? Because what you get is the same thing we were sort of talking about, is it depends on where you're looking, when you're looking, okay, and whether or not the gauge analysis has had any changes in it. So you get answers all over the place, right? Fundamentally, it says we look to be within about 20-25% on daily accumulations, but there's always scatter. Okay? We do it over Australia. We've got 5 or 6 of these different sites. But at the heart of this is still sort of this issue. This is a slightly different plot of the total error in terms of systematic versus random. So all the 3 different algorithms, they all add up to 100%. But what you see is that all these combined algorithms work really well over the central US, because to some extent they've always all been tuned there, okay? And then when you get away from the central US, none of them work quite as well, okay? And so then the systematic error starts to increase at the expense of random. But again, we're in the The biases are in the 10, 20% range, okay? Okay, so we've had ongoing campaigns, okay? I was accused once of saying, you know, with TRIM project, we had spent $3 million on validation, and none of the algorithms had changed a single line of code. So what was the problem with it, right? And I think after 20 years, it's sort of this realization, the algorithms were okay. We didn't know enough about the precip structures, okay, to properly interpret the validation results. So everybody's busy these days trying to figure out how to parse the validation data into similar meteorological conditions that should give consistent results irrespective of where the radar is. Okay? Nobody's gotten there yet. Okay? So this is an invitation to anybody who knows clouds to help us out. Radar networks are useful, but you know, different validation over different places, right? Okay. At certain really high quality validation sites, we've been able to get a little bit more out of it in terms of microphysics, but not enough to apply that globally. So, the last part of my talk is sort of a pivot we did. Say, okay, suppose we don't validate an individual radars. Let's just expand the problem, okay? We know that water is conserved, okay? So let's take these 5 tropical ocean boxes. Tropical ocean because we think we do better there than anywhere else, okay? So this is the best we can do. Tropical oceans because evaporation is not the most complicated there. Humidities are high, right? It's always about 80% over tropical oceans. You know, wind speeds over ocean are fairly well known. And evaporation really doesn't vary very much, okay? If you look at over time, it's pretty flat, okay? Water vapor divergence comes from era 5. We know era 5 has too much evaporation and too much precipitation, but about the same amount more than the obs. So we thought, yeah, maybe their, you know, divergence is about right, okay? But that's a guess, okay? So divergence from era 5 and then one of the precip products, right? So each of these boxes, you know, should be flat, okay? If all the products were good. Then we started this and somebody said, oh, you gotta move your tropical Indian Ocean box. The Indian dipole is such that you put the box right in the middle and whatever's going on, you're gonna be averaging it out, okay? And so when we first did this, the tropical Indian Ocean was a flat line, okay? It's the one we used to show that things were perfect. But then when we divide it into 2, neither side is perfect, okay? So now, next comes an animation. So it's gonna play a few times. So the first time I'm just gonna tell you what you're looking at and then you can sort of pay attention. So this is the box. Instead of just those 5 boxes, we're just gonna slide the box over, okay? And then there's a time series from 1998, the beginning of TRIM, to 2022, the end of this master's student when he defended, okay? Okay. No other reason, okay? So this is the lack of closure, okay? So when this goes below, there's not enough precipitation if you want to blame precip, and we're going to blame precip. When it goes above the line, there's too much precip, okay? It's only ocean, so when it comes over land, the line is gonna get funky, but because it's only looking at the bits that are over the ocean, with the area gets really small, okay? So ignore that, you know, massive thing that happens when you get over land, okay? So now when it comes over again, it's gonna start with Africa. Things are way out of phase, right? Because it's only that little bit of water. Then the Western Indian Ocean, things are pretty close to balanced, okay? Everybody's happy. East Indian, we start seeing numbers get really big, too much precip. Okay, then again, too much land to pay attention. But as we get into the West Pacific, you see there's this long trough where almost a millimeter out of balance for a long time. At the end, it starts to close, okay? So then Central Pacific, we see these bumps. East Pacific, things get pretty quiet again, okay? And then as we get into the Atlantic, you'll see the Atlantic is also really well balanced, okay? So the problem, the algorithms haven't changed throughout this, right? So if there's balance or imbalance, it's not a problem with the algorithm. It's the algorithms are not capturing something that's happening. So we're going to start looking at these. And before we do, we have to get one more concept because some of the biases I'm going to try to explain through that. A long time ago, graduate student Greg Elsasser, he's at NASA GIST these days, modeling clouds in the climate model, parameterizing them. We sort of looked at clouds, but from an ensemble. So this is 1 by 1 degree, each 1 by 1 degree box, right? He did histograms of the cloud heights in the box, put the amount of rainfall, the amount of convective rainfall in there, and then the histogram of the heights. And then we did a clustering, like everybody does, and we started out with, 3 clusters, 4, 5, 6, 7, 8, 9, 10, to see where things would, sort of self-separate. And it turns out precip just has 3 clusters, okay? I mean, there's a non-precip, but convective precip in the tropics, 3 clusters. Shallow convection, okay? This is the PDF of their heights. And it doesn't matter which basin you're in, okay? They all look more or less the same. And then what he called the mid-level cluster, we now call deep isolated cluster, okay? It still has a few shallow clouds in it, okay? That's still there, but clouds get higher. And then the deep organized cluster, right? So just about it really separates cleanly in the tropics from the sort of cloud height observations that you can explain most of that. Now, I'm not going to go into details, but essentially because of inhomogeneity, it's quite likely that the passive microwave is underestimating the precip in these two and overestimating the precip in that. Okay. And so on average, it's about right. As long the hypothesis, as long as the ratio of these things is about the same, everybody's happy. Okay. So now let's look. The easiest box turns out to be the Central Pacific. Okay. The Central Pacific Ocean, this was the closure line, okay, that we sort of scrolled through before. We now froze it to this location, right? And the blue boxes, the tropical Western, Eastern Pacific, and Atlantic, we're not going to look at anymore because they were perfect. And looking more at perfect things just makes them imperfect again. So let's not parse those into subsets, okay? Let's keep it. Okay, so tropical, this was the closure line. In these 3 lines, the blue line is the deep organized, and the green line is the shallow, okay? And the amount of rain that you get out of those. So of course you get much more heavier rain out of the organized, but it's not very common, right? So there's more rain from the shallow than the deep organized. So what you see is that every time you see an increase in the deep organized, there's a decrease in the shallow, and you get really close to, closing the water budget. The fact that the whole thing is a little bit below the line is probably less important, right? In that it's easy to make overall changes, right? That's one parameter. But there's really good correlation, when deep organized goes up, the shallow goes down, and we get much closer to convergence. Guess what? That's just the ENSO signal. Right? That's just the ENSO signal, except, okay. So you see it here. Every time there's an ENSO, you get deep organized convection. The water budget closes. When you get out of ENSO, it doesn't happen, right? So this is just a case where we actually can see, right, the closure or lack of closure has to do with the convective organization of storms. You can show that this is also correlated with the wind shear that helps organize these things. So it's all consistent. And we thought we were done until we looked at the tropical Western Pacific, right? And so in the tropical Western Pacific, it's warmer, and the shallow convection doesn't move very much, but you can see there's an interplay between the deep isolated and the deep organized convection. So over time, these lines wiggle, And if I just look at this part, I could tell the same story as before, right? I could tell the same story that when the deep organized increases and the deep isolated decreases, we get really close to convergence, and that happens during El Niños and otherwise not. But then you have this large period here, okay, where that's not the case. Deep organized is actually much lower, and we couldn't. It does not match with the ENSO at all. In fact, there's this whole period though where there's very little correlation. They get out of phase, and yet this line is flat. So we couldn't quite figure out what was happening in that region. Right? So it turns out that this this long term here is also the Pacific decadal oscillation, right? Which is playing in addition with that. And if you look at just the sea surface temperature, there's an anomalously warm period here when our method is not working, right? So this has more to do with a different pattern of SST warming, different shear. Okay, we don't have the low level shear that helps organize. There's deep shear in the column, but we're still working on what is it about the clouds during this period that was different that causes those biases. Finally, the tropical East Indian. Okay. You see this was the region where there was too much rain, and there's really no pattern in the deep isolated in the orange or the deep organized in the blue. They're pretty flat. If anything, there's a little bit of the shallow is sort of, the green is sort of matching the black a little bit, right? So this would sort of indicate that it's the shallow, changes in the shallow precipitation contribution here, but there's not that much shallow to begin with. And what's more is when the shallow increases, the rain should be decreasing. So it's going in the wrong direction, right? So none of our explanations work for the East Indian. Looking further, okay, when you look at the ice-rain ratio, so you look at the amount of rain, amount of ice per bucket of rain is what I call it, right? So it's just the integrated water path divided by the rain rate. That corresponds really well with a lack of closure, right? So it seems like in the East Pacific, the shallow precipitation in particular is starting to puts more ice in there. When it puts more ice in there, then we get better closure and vice versa. Right? So this is a different mechanism. It's not an organizational thing like with a deep organized and isolated. It has to do with the amount of ice and clouds. Okay? And that we're still also looking at why we think it has to do with actually radiative feedbacks in the Indian Ocean, which are sort of a bit different there than the other basins. Okay. But that's sort of the problems that we're dealing with today, is trying that next level of understanding of what causes. So my last slide is actually this. Products are getting close, if you go to 20%, they're pretty robust globally now. I did say where radars and radiometers are trustworthy, okay? That's a caveat so you don't walk away with a completely wrong understanding. There's a couple of places where we don't do well. Really high latitude oceans, okay? And that's because the radars we have don't quite see the rain, okay? They're not sensitive enough for drizzle. And the radiometers can't tell the difference between cloud water and drizzle. So they just say there's a bunch of water there. You can assign it to drizzle or cloud water any way you want to. So we're struggling with that a little bit at high latitude oceans. Not a big problem in the tropics or over land. Over land, remember the radiometers really needed ice to see the precip. So if the precip has no ice, radiometers don't see it. And so that's true for a lot of orographic precip. So orography is a problem. And high latitude oceanic precip is still a problem. Communities are working on that. Okay. The rest is fairly robust. Okay. These high resolution products are everywhere. They're easy to get. Validation though is difficult, right? because it changes from one location to another. And the water and energy balance studies, do provide a broader perspective on this, and we've been pushing hard on this. It allows you to learn something that validation experiments don't let you, right? In fact, one of the things we're advocating to NASA and other agencies now is to stop making climate data records of single variables, at least make them together, so people can see whether or not soil moisture actually increases when there's excess precip or not, right? So those very simple, relationships that nature ought to have that are currently just completely ignored. So with that, I thank you, and I'll stop.
Thank you, Dr. Is this on? Yes, it is. I'm a little confused because let's take an isolated convective cell. There's a fairly short life cycle to it, several hours, let's say, and the properties of the clouds and the precipitation are changing relative to each other over that time period. You go from shallow cloud to the deep cloud, and then you get heavy precip, and then when you get the big anvil in a short-lived, relatively isolated thing, the rain is mostly over. Yeah. So how do you take account of those kind of life cycle issues?
Yeah, so the precip missions always make sure they're non-sun synchronous, right? And these are all aggregate statistics. So it assumes that you've seen a random sample of each of those states, right? So you cannot, right, if you try to do this, what I just talked about, sort of on the cloud as it evolved, it wouldn't work, right? It does assume that you're going to come over randomly and that you're going to see, the cloud state in just in random parts, and that the biases will still show up after you average. Okay.
Chris, thank you for that talk. So NCAR's going to be building an airborne phased array radar with a Doppler instrument with polarimetric capability. Put it on a C-130 and we can fly it almost anywhere. How much would that help some of these problems, if at all?
Some of these, I would say, we're not quite ready for that, okay? We have these really large differences between regimes. And because we need to sample randomly, right? I don't think an aircraft right now can get enough random samples, right? So I say the aircraft is better for that instantaneous comparison with the radar, because there you can sort of directly match assumptions in the two products, right? But for these sort of global things, you can't get enough statistics fast enough, right? So I'd say that the key there is to compare it to the radar schemes that are making assumptions about drop size distributions to see if those physically are matching.
We have a question here from Silo. If money and time weren't obstacles, what kind of instrument analysis or validation efforts would you say is most important to implement to get the best improvements in global precipitation estimates?
So if money's not an object, I just take it and. But if it is an object, no. So in fact, with IPWG, what we started to address this very question, right? And that's without infinite budget, is to try to set some standards for what minimally ground-based radars ought to do to make a uniform rainfall product, so that we can get people from around the world to contribute, let's say, a year or 2 years of data. Doesn't have to be operational, doesn't have to be a huge network, but from as many different regimes as possible, right? So right now we're trying to figure out if these biases, is it because of convective organization, right? Is that in turn related to, right now we're chasing temperature and CAPE, as we'll sort of make the same clouds over and over again. That doesn't seem to be enough. We're not getting anywhere with it, okay? So what we like to have is sort of a broader database of different meteorological regimes that people can test their hypotheses on and say, when these large-scale conditions repeat, I seem to be getting, self-similar results. Then we can start, using the aircraft and say, is the result right or not? But right now, we're not getting the same results. So we're trying to establish sort of this global network of people who process with some commonality. So when I get, a different answer in a different location, I can be relatively certain it's the environment, it's not the way the data was processed.
Yeah, thank you, Chris. You talked a lot about average rainfall. Can you talk a little bit about like hourly rainfall distributions, PDFs? Because like my experience with GPMI merges, it has a lot of light rainfall into little extreme, and it also seems to smear out the rainfall over larger regions, which is probably a related problem.
Yeah, so it's about 30, I think. Let me, sorry. I lost the slide. Where was my, oh, it's here, it should be here, sorry. Six. Oh, sorry. This, okay. So when you look at the extremes, right, and that's sort of shorthand for PDF, right, you can see that the satellites too have fairly broad, right? So when it comes to extremes or the PDF, you actually have to know a little bit more than I talked about how the product is put together. For instance, if you use the iMerge PDF, well, it turns out a lot of their, extreme rainfall was this just arbitrary cutoff that they had built in, right? That no radiometer could ever give more than 50 millimeters an hour. And if you did that, then no IR could ever accumulate more. So those tend to be just artifacts, mechanical artifacts in the algorithms, not fundamental problems. Right? They should all be able to get PDFs right, but there's enough mechanics in the algorithm that all I can say is, you have to talk to one of the developers. It's not a universal issue of the merging. It's the nuts and bolts of what they're doing. Sorry.
Okay, let's take it around.
Thank you, Chris. Very nice talk. I just wondered, did you find any diurnal variation of the bias of satellite precipitation? Because I used to compare the precipitation in Tibetan Plateau and also the Maybe season. And what I found is that during the daytime, the GPM or trim precipitation is okay, but at night, they always lower estimate the precipitation. I just wonder, but you didn't mention here, United States, did you have the same?
Yeah, so the diurnal cycle issue has two parts, right? So the radars don't care what time of day it is, okay? The radiometers don't care what time of day it is, but obviously the precipitation does, right? So if there's a change in the precipitation characteristics, for instance, if during the night there's less ice, the clouds are shallower and there's less ice, right? Then the radiometers will miss more of that than they do during the day, right? So when there is a marked shift in the precipitation characteristics from day to night, you can end up with subtle biases, right? So it's not so much the algorithm as it is, again, I always blame the clouds, okay? It's the clouds' fault, right? If they just did what they're supposed to. So,
Yeah, because I know in May season, the precipitation at night are caused by most of them are caused by the elevated convection, and the physical mechanics is quite different with the daytime.
right, and so that, so that's typically what we're running into, right? And it's exactly the problem we're trying to solve now. It's like, so how do we know that that's a different cloud than during the day, so we don't mix them, right? So.
Okay, I think we're out of time. Thanks again, Chris.
Okay.
And please, everybody, join us for some cookies and coffees.